This is 7.5.6 transformers. So we'll start by drawing a direct current circuit with a cell and a transformer coil, which is the coil of wire, and a switch which allows us to turn the circuit on and off. And then next to that, we'll draw a second coil on a second circuit, and we'll have a galvanometer on there to measure the EMF that is produced. So if we were to close this circuit, then a current will flow through the first coil, and when a current flows through the first coil, that creates a magnetic field. That magnetic field will then be flux that goes through the second coil, and a changing magnetic flux in the second coil means that there's an EMF induced in the second coil. Now, this only happens because when you close a switch, the current does not instantaneously flow at its maximum value. Rather, it goes from zero up to its maximum value. And that happens very quickly. But if we were to watch in slow motion, we would be able to see that the current would increase. So as this current increases in coil 1, there is an increasing flux that's created by coil 1. And the flux from coil 1 becomes flux linkage in coil 2. And that changing flux linkage in coil 2 means that there's an induced EMF in coil 2. So our galvanometer will read some maximum value. After a very short amount of time, though, the current that's flowing through coil 1 then becomes stable, so it becomes a constant. And a constant current means that there'll be constant flux being generated by coil 1. And if there's a constant flux in coil 1, there's a constant flux linkage in coil 2. So no EMF is induced in coil 2, as the rate of change of flux linkage would remain constant. So that means that our galvanometer will then go back to reading 0 very quickly. So the way this will look in real life is you'll see a short deflection in the galvanometer, and very quickly that needle will return back to reading 0. If we then open the switch, the current drops from its maximum value to 0. Again, this is not instant. It might be very fast, but it's not instant. So in slow motion, we would see it drop. And as the current falls to 0, that means that there's a changing current, which means that there's a changing flux created by coil 1. And if there's a changing flux created by coil 1, then that means that there's a changing flux linkage in coil 2. And if there's a changing flux linkage in coil 2, then there's another EMF induced in coil 2. However, this time we need to remember that the current, when it changed, it had a negative delta rather than a positive delta as the current decreased. So the magnetic field that was induced from coil 1 was the opposite to when the switch was closed. So in this case, the EMF, which is induced in coil 2, is opposite to that of coil when the switch was first closed. So we get a negative reading. Now that the current is 0 in coil 1, there is no flux being generated by coil 1, and hence there is also no flux linkage in coil 2, and there's also no changing of flux linkage. So if there's no rate of change of flux linkage in coil 2, then there's no induced EMF, and our galvanometer then returns back to reading 0 again. So looking at this, we can see that if we use a direct current, other than when you switch on and switch off, there is no change in current. And if there is no change in current, then the transformers do not function. So this tells us that transformers only work with alternating currents. So we're going to look at a common example of a transformer, which is called a step-up transformer. Step-up transformers increase the voltage and give you a higher output voltage than the input voltage. So we're going to draw another circuit. This time we're going to have an input coil that's connected to an AC source. That primary coil then will be linked to a secondary coil using an iron core. And then we will have an alternating output in the secondary coils as well, which will also be AC. Now, step-up transformer has more secondary coils than the primary coils. So you're about to see that the way that I draw it is I draw many, many more coils in the secondary to emphasize this fact. So I've labeled the primary as the input and the secondary coils as the output. And what you see in the middle linking the two of them is an iron core. Now, the iron core is a soft magnetic material, which basically means that in the presence of another magnetic field, it will create its own magnetic field, or its magnetic field will be induced to be the same as the field that created it. When the original magnetic field is removed, so when the input coil is switched off, then the magnetic field of the iron core will cease to exist. The iron core is also laminated, which means that it's made in strips rather than one solid material. I'm going to label the input here as alternating with a voltage called V primary. And what comes out of the secondary is also alternating, and we'll call that V secondary. So alternating current in primary coil produces a changing magnetic flux. And if there's a changing magnetic flux in the primary coil, then there's a changing flux linkage in the secondary coil. And this is linked together by the iron core. So I said two things about the iron core. I said that number one, the iron core is soft. So soft magnetic materials, we're not talking about it being squishy, but rather soft magnetic materials become induced magnets in the presence of another magnetic field. So when the primary coil becomes magnetized, when there's a current flowing through it and it induces a magnetic field, the soft iron core copies its magnetic field. It aligns its domain so that it creates an identical magnetic field as that from the primary coil. That increases the flux density. So it creates a stronger magnetic field, and it directs that flux to the secondary coil. So it increases our flux linkage. So because of that, there is a changing flux linkage in secondary coil, which induces an alternating EMF. Now the core does a couple things. And one of its primary purposes is to reduce losses, so to make the whole system more efficient. Number one, being laminated. So if the core is laminated, it's made in strips rather than one solid material. Making the core in strips reduces the eddy currents that are induced within the core itself. So some currents will be induced within the core and wasted. But making them into strips rather than one solid core reduces that. And B, we use a soft iron core, and that reduces hysteresis losses. In the iron core. Finally, we've got transformer equations. So V primary over V secondary is equal to the ratio of the number of turns in the primary over the number of turns in the secondary. Put a box around that. So V is voltage in volts, and N is number of turns. And then for efficiency, the efficiency eta is power out over power in times by 100%. And if you can do it in power, you can do it in energy. If you can do it in energy and power, you can also do it in IV. So I out, V out over I in, V in times by 100%. And efficiency doesn't need to be given as a percentage, it can be given in decimal form as well. So in decimal form, you simply won't put the 100% in. And that's the end of 7.5.6.